Well, thank you, Ari, and thank you for inviting me this time, anyway. And thank you certainly to this, as Ari says, dedicated audience devoting their Saturday morning to this. It's much appreciated. I started off the essay that I wrote for the book for the festival by talking about this glorious landscape of the Australian desert. These are the hills not too far from Uluru. These are the hills that are called the Olgas. A beautiful landscape, but that's not really their name. That was the name given to them in the great tradition of colonial patronage, named after a queen of Württemberg, I think. Their real name is Katajuta, which means many heads. And I think you can see how descriptive that term is. These are sacred to the local Aboriginal peoples. They're home of the snake ancestor, Wanambi. And there are stories, endless stories, that the local Aboriginal people have about these hills. And I suggested that geologists and Aboriginal peoples view the landscape in very similar ways. Because as far as we're all concerned, a landscape tells a story. It tells a story of time, it tells a story of change, it tells a story of what's happening today, and it hints at stories of the future. And stories on every scale. A single grain of sand tells a story. Very often, an immensely long story from geological deep time. And so we share an imagination about the landscape. If you like, share a geologic imagination about the landscape. Landscapes that tell stories of the past and, as I say, hint at the future. Aboriginal peoples incorporate the landscape into their spiritual world. Geologists translate the landscape through the process, and here I borrowed a phrase from that wonderful scientist and writer about science, Peter Medawar, who described science as the process of poetry and bookkeeping. And so geologists do the bookkeeping, they do the slogging around of those hills, the examination of the rocks, the taking samples, taking them back to the laboratory. That's the bookkeeping. It's inevitable, it's important. But then the understanding and the interpretation of that is the poetry of science, of geology and of any science. We tend to look at the landscape from different perspectives, and through this, we geologists build the geological map. This is the geological map of Katajuta. And that is a documentation of all that bookkeeping, all that hard work. And it's if you like, it's the sort of geological artist's expression of the stories that landscape tell. And it's the same, this is a landscape east of Katajuta, in itself a beautiful work of art that our planet has produced, and in a sense, the geological map of that landscape is in itself a work of art as well as a scientific document and a storytelling device in itself. And I think it's worth mentioning that this year, 2015, is the 200th anniversary of the first real geological map. It was produced, the geological map of England and Wales, it was produced in 1815 by William Smith. He was surveying the country for canal construction and began to put together the geological story of the landscapes that he was working in and excavating. And he produced this beautiful map, which was a supreme act of poetry and bookkeeping. And if you look at the version of that map today, you can see just how accurate William Smith was 200 years ago. Today, we're making geological maps of Mars. we can make a geological map of Europe. This is the way geologists see Europe. It tells the stories of the development of the continent, of the oceans, of the histories of the Alps and the other mountains of Europe, of the Mediterranean basin. It's full of stories, is that geological map of Europe. But in the last 50 years, our view of the world has changed substantially. As Lucas and Ari have written in the introduction to this festival and to the book, the advent of photographs and images from satellites and from space has dramatically transformed our understanding of our own planet. As they said in their introduction, they said, these images have spawned a new ecological consciousness simply because we could see our planet from outer space. And now, not only does satellite imagery underpin our thinking about the Anthropocene, as we'll see a little bit later, but it also just illustrates for us the sheer beauty, the sheer art of our own planet. Whether it's river systems, deserts, sand dunes, river deltas, salt deserts, or the extraordinary sculptures of the underwater landscapes of the sand shoals of the Bahamas. These are extraordinary images. And in this talk, I'll be addressing just one aspect of these landscapes, one often unappreciated aspect of the questions raised by the theme of this festival. That is, how do we understand the systems and processes of nature and our intentions and interactions with the planet? In many senses, for those of you who are here on Thursday morning, I'll be taking off from the kinds of descriptions that Mark Williams gave us about changes to the biosphere and changes to rivers during the Anthropocene. I'll be taking off particularly on that latter part and really asking the question, as we are geologic agents, human beings are geologic agents, and how can we see how that agency has modified the surface of the planet? This is, yes, poetry and bookkeeping, but I should warn you, a couple of warnings here. There will be quite a bit of bookkeeping in this talk. There will be a couple of graphs, there'll be some numbers, but it's important. It's the only way in which we can come to grips with the questions about the Anthropocene. Part of that bookkeeping is another warning. I'll be talking quite a lot about gigatons. We'll come back to exactly how we think about a gigaton. What I won't be doing is wondering whether gigatons are hyperobjects. I suspect they probably are, but that's just my view. And I won't be worrying too much, in fact, at all, about the ontology of the gigaton. The key to all this satellite imagery is not only what we see in a single time frame, a single glimpse, but the fact that with the span of time that we've been obtaining satellite images of our planet, we can literally see change. We can measure, monitor, analyze, and wonder at the changes over time. We've added now the dimension of time. Now, the image for this festival, the image on the book, the image that was here before I began to talk, was that of the Aral Sea. And in these series of images, we can see the changes to the Aral. Oops, sorry, no. Pressing the wrong button. There we are. Pointer. We can see the changes to the Aral Sea from 1977 to just a couple of years ago. This is, of course, and that's why the image is there for the festival, This is one of the great environmental tragedies of our times, the fact that in a space of 40, 50 years, a great and thriving inland sea, together with its ecosystems and its societies, has been destroyed by the absurdity of trying to grow cotton in the middle of the Central Asian desert. We can follow changes, for example, in the growth here of Las Vegas, again in the last 30 years or so. From a small development, it was a small city that never should have been there to begin with, again in the desert, to, in today's, 2009, to a gigantic metropolis with endless swimming pools and golf courses and just an absurdity in the middle of the desert. We can look, for example, in the last 30 years in the deserts of Saudi Arabia. Here in 1986, a landscape, a desert landscape, essentially unaffected by human beings. And yet in 2013, here is this intense agriculture. Each of these is one of those rotating irrigation arms, forming circles within which the crops are grown, which has completely changed the landscape and, of course, completely undermined the water availability in that part of Saudi Arabia. And then finally here, this is Cape Cod in Massachusetts in the United States. Changes again over 30 years, between 1984 and 2014. And although it is influenced by human activity, it's not a particularly intensive human interference. What we're seeing here is the natural dynamics of the coast. The coast is the most dynamic natural environment that we have. And in those coastal environments, the barrier island, the buildup of sand off the coast is the most dynamic of those coastal environments. And just in the space of 30 years, we can see the changes as a result of essentially the natural processes of coastal currents, waves, tides, storms, where that barrier island system has been completely modified, but naturally. And down here, we can see the dramatic change in just the shape of those barrier islands. And yep, sand is the most dynamic geological material of all, and it's a material that participates constantly in the great game of landscape change around our planet. In the last 5 minutes since I started talking, countless thousands and thousands of tons of sand and mud have been moved around the surface of the planet by rivers, bringing those sediments down to the sea, and then they are redistributed by coastal processes. It is happening every second, every minute of the day on every part of every coast of the world. And then there's also, as part of this great game of global sediments and sediment transport, is dust. Huge volumes of dust, particularly from North Africa, crossing the Atlantic, fertilizing the Amazon rainforest, building the soils of the Bahamas, but at the same time carrying bacteria, good and bad, and toxins. The atmospheric dust system is an extraordinary and complex system. So what does this what we call a global sediment flux, what does it look like? Here's a simplified map of the world's rivers, and here's an example of a river carrying sediment to the sea. Now, how can we quantify this? It is estimated through reasonable scientific analysis that every year the rivers of the world transport 13 gigatons of sediment to the oceans. And note that that number applies only to the easily measured sediment in a river, and that is the sediment that's fine enough to be suspended in the water. It doesn't count in that number the boulders and the coarser material that is rumbled and rolled along the bottom of the river. But what can I possibly be talking about here? These gigatons. What does a gigaton look like? Well, here's one analogy. 13 gigatons is enough to build 32 Great Walls of China. It's a dramatic analogy, but I don't know about you, it doesn't help very much visualize it. Let's look at something that's maybe a little easier. Let's look at a simple, normal, average dump truck. We see them every day. Those 13 gigatons would take 650 million dump trucks to transport. If we were standing by the side of the road and this row of dump trucks started driving by at the rate of 10 a minute, we'd be standing by the side of the road for over 100 years before the annual sediment flux had passed us. It's an enormous scale of natural processes. And then, just to refer back to dust, 15 million dump trucks of dust being transported around the atmosphere every year. So let's just look a little bit about how these systems work. And here I've taken Monterey Bay in California as an example. The sediments originate in the hills as a result of weathering and erosion, and of course gravity carries them down into streams and rivers, eventually to the coast. But not all of the sediment that's derived from the mountains actually arrives at the coast. It's trapped in a river's floodplain. It's left behind where the river channel naturally moves back and forth and so on. But what does arrive at the coast is then transported by longshore currents that are parallel to the coast, by waves, and it's also those sediments are joined by the detritus from cliffs along the coast. And so we start building up what we can call a view of sediment budgets. And a sediment budget is just like any other budget. It has incomings and outgoings. And anywhere on here, at any given point, we could stand and measure the sediment budget, the amount of sediment that's coming in to where we are and the amount of sediment that is flowing out. And that those sediment budgets are part of these grand sediment transport systems, which along the coast we call littoral cells. And we can see they can be quite complex because here in Monterey Bay, the northern part is sediment being carried along the coast and then down to this point. Southern Monterey Bay, it's along the coast and up northward to this point. And at this point, where the main rivers come in and those two littoral cells meet, that sediment is then flushed down this extraordinarily huge submarine feature, the Monterey Bay Canyon, flushed out into the Pacific and essentially lost from the system. So that the Pacific in that case is a sink, is a sediment sink compared to the sediment source, and roughly 25,000 dump trucks of sediment are simply flushed down into the Pacific every year. So we have very distinct sediment systems, littoral cells, sediment budgets, and so on. But at the northern end, if we look at the northern end of this image, we see a slight problem with the natural system, and that is called the city of Santa Cruz. Here's the city of Santa Cruz. We can see this, remember, sand will be transported along the coast in this direction, but unfortunately we've done a number of things ourselves to interfere with this sediment transport. We've basically barricaded rivers so they're no longer working naturally. We've built structures out into the ocean so that the sand builds up here, and downstream, down from that, the flow of sand, the supply of sand is depleted. We have here, just on a local level, profoundly changed the natural landscape. It's the same, rather more locally, to where we are today. This is Amsterdam Harbor. We can see the massive disruption to the movement of sand along the coast and the massive constraints that we've placed on the river. So there are two questions. What is the anthropogenic influence on global sediment flux? We'll look at that. We'll see that it's extremely significant. And secondly, is it a tangible symptom of the Anthropocene? And I think the answer to that is an emphatic yes. The current sediment flux from rivers we just saw was 13 gigatons a year, approximately. We can also, through looking at the history of sedimentation, the history of rivers, come up with an estimate of what is sometimes called the pristine, or we can call it the pre-Anthropocene sediment flux. Let's say about 1700 for this purposes. I'm not trying to formally define the beginning of the Anthropocene, but I'm saying that before there was profound influence by mankind on sediment flux, it was probably around 15 gigatons a year. So we've decreased it by a couple. Not very much, not terribly important, you would say. But behind those figures are some extremely interesting, dramatic, and in many ways disturbing facts. First of all, because there are ways in which we have increased the sediment flux into the oceans. We've increased it dramatically, and indeed, since about 1900, we've increased it rampantly through deforestation, which increases erosion and the flow of sediment, and agriculture, which does exactly the same thing. We've increased sediment flux through messing around with rivers, and we've increased sediment flux through the scale of our digging around in the surface of the earth and these gigantic mines. But at the same time, we've decreased sediment flux largely by building dams. And the scale of dam building over the last 100, 150 years is actually quite astonishing. If we define a large dam as one that is taller than 15 meters, then there are more than 40,000 of them worldwide. And they're all recent constructions. Here's the United States. In 1950, there were very few dams. By now, there are more than 75,000 dams of every size in the United States. It's an astonishing act of construction and water management and sediment management. So what we have done, we've increased the amount of sediment going to the oceans in one sense, and we've decreased it by trapping it in the reservoirs behind each and every one of those dams. How can we make an estimate of how much sediment is trapped behind the world's dams? Well, it's not easy because, of course, it's hidden. It's in the reservoir. It's below the water level. But there are occasions, for example, here, where for environmental restitution, reconstruction, a dam will be removed, and we can see what was behind it. This is the Elwha River in Washington State in the northwestern US. It's a relatively modest river. It's only about 70 kilometers long. It's not a great river. But here, this dam was removed, the water drained out, and we can see the sediments that had accumulated in the valley behind it. Those sediments are now being flushed down the valley, and they are building out at the ocean into an entirely new delta. And so we can estimate the rate at which that's happening and the amount of sediment that was trapped behind the dam. And in this case, for a relatively modest river, it's about 3 million dump trucks. Now, if you start escalating that to the large dams and every dam in the world, the figures add up very, very significantly. The estimates, although because counting every dam in the world is impossible, and the estimates of whether that dam is trapping all of the sediment behind it and so on is not always easy to make. So the estimates vary quite widely. between 5 and 60 gigatons trapped every year behind the world's dams. So let's take a modest mid-number. That's 25 gigatons of sediment trapped every year. If all of that were liberated from those dams and reservoirs, it wouldn't all make it to the ocean, as we've seen. Some of it gets trapped in floodplains and when rivers change. So let's say that the reduction is actually 14 gigatons out of those 25. That means that the current flux, in the absence of dams, if there weren't any dams, the current flux of sediment to the oceans would be 14 plus the 13, which is we know is already happening. That's 27 gigatons of sediment per year. And that's roughly twice the pre-Anthropocene flux of sediment to the ocean. That's twice the effect of erosion and landscape change and so on that was happening pre-Anthropocene. And so the fact that we had 13 gigatons today and 15 gigatons before 1700 is disguising this dramatic fact that we have actually increased the rate of landscape change by a factor of at least 2. We can see that we can actually begin to reconstruct over time and note that this is years ago, but it's a logarithmic scale. Here's 1,000, 100, 10 years, and today. And up here is the sediment flux, the sediment load of that river. The number 1 corresponds to the pre-Anthropocene level of sediment transport. 10 is 10 times that, or 100 times, or 1/10 and 1/100th. And we can see different rivers have behaved over time, and the key time here is really 100 years ago or so up to the present. Some rivers, the Nile, the Colorado, the Indus and Danube and so on, basically our influence has reduced the amount of sediment they carry to the oceans extremely dramatically, and it also reduces the amount of water they carry. The Indus River 50 years ago was transporting 100 billion cubic meters of water per year to the Indian Ocean. 100 billion. Today, it's about 10. The sediment that the Indus River transported was around 250 million tons a year. 250, it's now 13. We have profoundly changed the systems of these rivers. But unfortunately, of course, what was happening during this period, 100 years ago, was when we were building cities and infrastructure on those rivers. I say unfortunately because, of course, that's what's causing these changes, but also we're building cities on a delta or whatever, which is no longer supplied by the sediment it needed when we built that city. There are other rivers, such as here the Yellow River, that over time, over human history, have dramatically increased the sediment load that they're carrying, and then through various factors decreased it back today, in part because of dams. The Yellow River is an interesting example. It rises in Tibet. It flows through this area called the Loess Plateau. Now, loess is a strange geological material. It's a very fine-grained silt that's blown by the wind and accumulates during the glacial periods. But it forms this tremendous plateau of very fragile but highly fertile hills. And so there was a huge amount of agriculture over the Loess Plateau that contributed to that massive increase in the amount of sediment that the river carried. And today, here's just one small sector of the Yellow River. It's the second biggest river in China. You can see just over this is just a few kilometers, there's 2 dams already on that river. And this, from an analysis from Wang and others in 2007, is again, here's time, pre-Anthropocene, huge agriculture deforestation influence of erosion and sedimentation, and then decreased down to today. And he attributes that decrease to 30% of it is as a result of reduced precipitation over that time, less rainfall, less erosion. 40% of it to soil conservation practices, and now the Chinese are very proud of their soil conservation practices, and I suspect that's a slight exaggeration. But 30% of that decrease is because of the dams that have been built on the Yellow River. And then we look downstream to where the Yellow River enters the sea. These are the channels of the river over historical time, and we can see the rate at which they've moved. Those channels have migrated back and forth over hundreds of kilometers. During historical time, the Yellow River used to enter into the Yellow Sea, empty into the Yellow Sea. It now empties into the Bohai Sea, and this movement of channels has been dramatically constrained by construction. I mean, this is the heartland of China. There are hundreds of millions of people that live here, and the construction and the infrastructure is incredible. But that construction has dramatically changed over time the form and behavior of the delta of the Yellow River. And then let's look a little bit further south at the greatest river in China, the Yangtze. The Yangtze River catchment area, in which all water and sediment comes from, is enormous. It's 50,000 dams in that catchment area alone. The famous one, of course, is the Three Gorges Dam, recently completed. But there are also 20 large dams under construction. Now, here's the problem. Down at the mouth of the Yangtze River, the delta, this is Shanghai. Now, Shanghai has been subsiding because of water withdrawal for 100 years, but it's getting worse simply because the dams on the Yangtze River have reduced the sediment supply to maintain that delta, reduced it to about a fifth of what it was 50 years ago. And so we find ourselves, I mean, the Niger Delta in West Africa is sinking at about 10 centimeters every year. That's that much. Every year. As a result of water removal and subsidence, and as a result of choking off the natural supply of sediment. But China is just rampantly building dams. This is a slightly opaque picture, well, because it's in Chinese, but this is a map of all the recently completed and under construction dams in China. There are just thousands of dams being built. The Chinese hydrologists are quoted as saying, well, every river that carries water out of China is a waste of China's water. The trouble is, of course, those rivers also bring the water to Vietnam, Laos, Thailand, Myanmar, Bangladesh, Bhutan, Nepal, India, and Pakistan. And so these dams here are profoundly affecting the water supply and the whole country's water management of those neighboring countries. So dams are the primary and substantial reason for reducing sediment flow from rivers. But we should also remember that sand mining in those rivers, sand mining for construction sand mining for the minerals that are contained in those sands, valuable iron and titanium-rich minerals, and so on. The mining of that sand is also removing hundreds of millions of tons from those two river systems in China every year. And most of it's illegal. Most of it is just run completely illegally by local sand mafias. I mean, it's difficult to imagine the idea that there is an illegal trade in sand, but it is on an enormous scale, and it is run by criminal mafias. It's supplied Singapore with huge volumes of sand over the last 20 years just to build Singapore. And it's all come from places like Indonesia, Malaysia, Cambodia, Vietnam. And most of it was mined illegally. profoundly changing the environment of those river systems and the health of the societies and ecosystems that we're talking about. And it's not just in China, it's a global problem. The global illegal sand trade is on a phenomenal scale. Nobody knows exactly what it is because it's illegal and you can't get at the numbers. But I mean, there are, and for example, in India, there are some hugely rich mineral sands along the coast, along the beaches. And these are just wantonly removed by criminal gangs. But I mean, you can't put a policeman on every beach. You can have the regulations, but you can't enforce them. And then, of course, there's the official dredging, which I'm sure Rob Holmes will allude to a little bit more. The ridiculous process of what we call beach nourishment. Hundreds of millions of tons of sand dredged from the sea, pumped back onto the beaches of eastern United States every year, just to replenish beaches lost because we've screwed up the sediment budget of those beaches. Sediment dredging and sediment used to build islands. I mean, as we speak, China is building islands in the sea to establish its new frontiers. It's building islands in internationally disputed waters as far as international boundaries are concerned. So what's it doing? It's building islands. Now, where does a lot of this sand go? Of course, the sand actually goes for some good uses, which we'll finish up with in a moment. But it also goes to what we might define as monstrous absurdities. And of course, this is Dubai. These are the developments of the palms in the world. There's one of the palms. Just constructing the foundations there took 3 gigatons. Now remember, 13 gigatons, all the rivers of the world. These things they took 3 gigatons of sand out of the local marine environment and dumped them there to build these developments. And that doesn't even include all the sand they had to import from Australia in order to build the concrete for the buildings in Dubai. Because desert sand doesn't work for concrete. Here's an extraordinary historical analysis by Krausman and others from a couple of years ago. This is the stuff that is transported around the world. Biomass, that's wood and coal and so on. Oh, sorry, coal is fossil energy carriers, ores and industrial minerals. Construction materials, that's sand and gravel, basically. From 1900 to 2009. The sheer growth in the amount of sand and gravel that we take out of one place and transport it to somewhere else is phenomenal, and that's about 30 gigatons every year. We use about 26 gigatons, 26, remember that's 2 times the 13, 26 gigatons per year of sand and gravel for concrete. That's 1.3 billion dump trucks. You'd have to stand by the side of the road for 200 years. And what are we doing with that sand when we put it into concrete and build something? We are locking it away. We have absolutely, on quite a significant timescale, and certainly way beyond our timescale, we've taken it out of the natural environment and we've locked it away in concrete. These kinds of problems, this is a slight commercial here. A couple of years ago, the French documentary filmmaker Denis Delestrac approached me to help him with a documentary on the global issues of sand, illegal sand trade, the loss of sand and so on, and the effect on the environment. And he made this documentary called Sand Wars, which I contributed to. And it's an award-winning documentary. It's worth seeing. It's just incredibly surprising, the scale of our landscape change and our environmental and social change as a result of sand mining. So to finish up here, we've looked at some of the poetry and the art of our own planet, the natural art. And we have, I'm sorry, but we have, I must admit, dwelt a lot on bookkeeping. But the bookkeeping is critical if we're to understand what we're doing. And a couple of conclusions, that the Anthropocene is marked by an irrevocable, well, when I say irrevocable, I mean on anything that we can conceive as our timescale. Irrevocable and massive disruption to the Earth's sediment budgets. And that sand, humble, everyday, regular old sand, is arguably an unsustainable resource because we rely for our way of life on just not any old sand but the sand the kind of sand, the special sand we need to put into concrete, the special sand that we need to extract titanium from to make the white paint for our refrigerators. We rely on specialist sands, not just any old sands, and we are locking them away from their natural habitat, their natural environment. So, I mean, I would say that we can't escape the Anthropocene. It's just inescapable. But the question we should ask is, how can we create a different kind of engagement and a way of thinking about our planet and ourselves that builds at least a better Anthropocene, one that is less anthropocentric and, I would say, less ethnocentric. Because let's face it, the whole concept of the Anthropocene and the primary influence on creating the Anthropocene is us as essentially Western culture. And I would be really interested to know if anybody had talked to an Australian Aboriginal person, a Navajo, Native American, a Tuareg from Mali. Has anybody talked to them about what they think of the Anthropocene? So thank you.